Hi, my name is Krishna, and I'm going to summarize this paper, Attention-Based LSTMs for Aspect Level Sentiment Classification. This is a paper by Yequan Wang et al. That was published in 2016 Conference on Empirical Methods in NLP. So this is the agenda for the presentation. So because this paper talks about attention-based LSTMs, I want to start off with what RNNs are, what LSTMs are, and then get into what is attention, what problem it solves, and then get into the actual details of the paper. We'll talk about aspect, key contribution of the paper, the results and methodology, and then we'll look at the some of my opinion about the paper, as well as uh, some thoughts on how we could improve the performance. So let's look at RNNs. RNNs stand for recurrent neural networks, and these are primarily used in sequence-to-sequence models. So for example, if we have um, 10-word sentence, so each word's encoding embedded vector is passed on to a regular neural network, a single layer, or it can be a deep layer as well, and that produces the hidden layer output, as well as is also passed on to the next activation layer. So what this does is the word 2 activation learns the features of word 2 as well as word 1. So that way, when a sentence is formed at the end, uh, this hidden layer output has learned features from all the words that came before it. So, and that is passed on to a softmax layer for output. But then there are some problems with RNNs. That is, all these red lines is the represent the backpropagation, the error backpropagation. But when it's a long sentence and there are many words that are in a sequence, and when the error is small, the errors that are learned by the activation layers at the beginning will be negligible because of because of the vanishing gradients. Now LSTMs is a way to address this issue. Let's look at LSTMs next. So LSTM stands for long short-term memory, and an LSTM block addresses this challenge by having by modifying the regular multi-layered neural network. That is, it the main feature of LSTM block are these three gates. Uh, F stands for forget gate, I stands for input gate, O stands for output gate. So what it does is the information is captured in a block called cell, and let me, yeah. So so what happens here is the hidden layer output of say W2 learns from like we saw in the previous slide, from word 2 features as well as word 1, but these gates kind of control whether it should learn from the previous hidden cell or from the current cell. So that way LSTMs kind of make it easy to have an identity, make it easy for the identity information to be passed to pass through multiple layers. So even if we have a long network, long RNN, it is still possible that the cell at word n can have information that is coming from word 1, and it's all controlled by these 3 gates. So so uh, yeah, and now let's look at the what is the need for attention. Consider this sentence: a boy went to the market and saw his friend there. The word his is dependent upon the word boy. Now, and if it was a regular feed forward neural network, the information about boy may not be fully passed on to by the time the neural network is processing this word. So what the way attention works is uh, kind of has a weighting factor where each cell decides whether so that the weighting function decides whether each cell should learn from uh, a cell that was a few layers behind it. So it's basically, so that's also the reason why it's called attention. Now, that brings us to um, the the core issue that is being addressed by this paper. That is, what is aspect? Now, aspect is a sub part of a sentence. For example, if you look at this sentence, a review, which says the appetizers are okay, but the service is slow. So the sentiment is the overall sentiment of the whole sentence can maybe neutral or maybe negative, but if we look by the aspect, food, the appetizers are okay, they're not bad, they're neutral, but the service is low, the service is negative. So what aspect helps us to do is uh, do a more fine-grained analysis of a sentence of text. So and this is the again aspect that the paper wants to address. Yeah, yeah. Now, this is the key contribution of the paper. We have seen LSTM and feed-forward LSTM network in the previous slides. The unique addition of this paper is, if you see these VA, and it's the same VA across the network. So what it does is there is an additional layer of embedding, excuse me, of aspect embedding that is kind of concatenated or appended to the word vector or to the hidden layer output. So thereby this aspect is kind of shared across the whole sentence. So if we are talking about if you want to understand the sentiment related to food, for example, uh, when we pass that aspect food, that we want to understand the sentiment related to the aspect food in that example sentence that we saw before, the output is it has a kind of is kind of weighted by the aspect of food because of the presence of these aspect embeddings. Now the paper presents 3 different variations of how this aspect can be embedded. The first one is the paper calls it aspect embedded LSTMs. So the aspect, like it said, aspect is added to the hidden layer output, and then there is attention based LSTM. So there the this kind of aspect embedding is added to the word vectors here, and then there is the combination, the everything model, which is aspect embedding, attention based and aspect embedding LSTM, which is what we see here. So we can see that the aspect is added to both the hidden layer output as well as the word input. So the intuition behind this kind of embedding is that when these LSTM networks are learning the features of the input, it's kind of weighted by the aspect. If you're talking about food, there is a food weight added to each of the words, and that is shared across the sentence. And if you're talking about, say, the service aspect, again, the whole sentence is kind of weighted by the service aspect. And so the LSTM, so the network here learns the features in the context of the aspect. I think it's a wonderful idea, and the paper claims that this is the first time someone has thought about embedding aspect in the word representations as well as in the hidden layer aspects, which is very, very innovative. And simple calculations here. So what this means is when we're trying to compute the softmax output here, we are doing that with a combined matrix. So you see, this is the weights for the hidden layer outputs, and this is the weighted aspect embeddings, and those are multiplied by en. That is, if we have an n a vector of length n, for example, if you are doing a 10 word RNN, so which basically takes in the sentences in lengths of 10. So we are just multiplying that by 10, so that the whole sentence, all the 10 words and their features get the same embedding. And this is all so the key learning, the additional learning that is happening here is that the network is learning these embeddings. That is, the network is basically learning the embeddings, so that based on the training data, the network will learn how to process or how to weigh those aspects. Let's look at some more details next. Just a look at the parameters. The basic LSTM has, like we said in one of the previous slides, there is the input gate, which monitors whether the information has to be passed on to the current cell, and then there is the forget gate, which monitors the information coming from the learning and the learning that is coming from the previous cells, previous layers, and then the output gate, which is basically weighing the final output of that layer, and then there are the memory cell values, and then the final sentence output. So just to and then the additional parameters that are added by this architecture, the aspect embedded architecture, are the aspect embeddings. So it's basically dimension A by the length of the n, the length of aspects. That is the number of aspects that we have. So for example, if we want to train a corpus on, say, 10 different aspects: food, service, cleanliness, rush hour, price, and so on. So the aspect matrix would be dimension would be say 300 sized vector. So 300 by 5 or 10. You know, how many ever aspects that we want to capture. We want this network to learn. So that's it. Let's look at the results first. The methodology follows, but I just wanted to present the results of the paper first. So the authors are comparing the performance of the three different models, architectures that I mentioned against some of the more standard networks, mainly LSTM, and then TD stands for target dependent, and TC stands for target connection. Both are supervised learnings, but the drawback there is that they do not have a way to learn the aspect level features. Clearly we can see that the three models proposed by these authors has a better performance, and as is predicted, larger network learns better and performs better. So we see that the ATAE LSTM, which is aspect embedded LSTM, works better. Some of the qualitative results, I'm not sure if this is clearly visible, but I can read it out. So there is a sentence which says, I have to say they have one of the fastest delivery times in the city. And we can see that because of the aspect embedding, the three words here, fastest delivery times, are having the highest activations. So which is also a measure of saying that the aspect embedding is kind of working, because it's able to pick up the words that are related to the aspect. Similarly here, it says the fajita we tried was tasteless and burned, and the mole sauce was way too sweet. Okay, so the related words, the related words in the sentence have kind of similar activations, and yeah. And this is the example that we saw in the one of the beginning slides on aspect. So again, another summarization. Appetizers are okay, so the aspect is food, polarity is neutral, service is slow, so service is aspect, polarity is negative. We can see that in multiple centers. Another important aspect of this network is that it's able to learn fairly long and complex sentences. For example, this sentence has 3 or more parts, and is still able to identify the aspect level sentiment classification. So for example, let's spend one more minute on this example, because this has multiple polarities. So there is a positive polarity, there are 2 positive polarities, and then there is a negative polarity. If it was a non-aspect embedding LSTM, it's possible that the whole sentence will be maybe classified as positive, because there are 2 positives, and the way network learns, it's possible the same polarity is assigned to the whole sentence. But because of this aspect embedding, the network is able to do a fine-grained analysis of the aspects. So let's talk about the methodology and training approach that the authors have followed. The data used is SEMEVAL 2014 data, and that has aspect level labeling for just one task, only for restaurant, the aspect restaurants has the aspect level labels. So that was used for the training. And the word embedding was so the words were pre-embedded, they were pre-processed, all the words in from the training data, and that was done using glove methodology. That will be outside the scope of this paper, so I'm not going to into that, but it was trained on a corpus of about 8.4 billion words, so which means that it would have learned the embeddings very well. The rest of the parameters, all the parameters that we have listed in like 2 slides before, were all randomized, initialized randomly. And yeah, all word vectors, aspect embeddings, and hidden layers are vectors of size 300. Here are some of the hyperparameters that the authors followed. Batch size is 25, momentum 0.9, L2 regularization, and 0.01 for AutoGrad. Here, so the aspects that are that the authors followed are as follows. FO stands for food aspect, PR is price, SE is service, AM is ambience, and AN is anecdotal or miscellaneous. So from the SEMEVAL data, the restaurants information had these kind of aspect level labeling, which was used for the author's research. So I'd like to talk about what I think about the paper. I actually felt that the accuracy improvement was not very significant, because if you remember the table, that the results table that we saw before, TC LSTM was already at 89.2 in the positive and negative classification, and ATAE LSTM, their everything model, has about 89.9 accuracy. And as it is, one of the problem with LSTMs is that they are computationally very expensive, because of so many gates and weights parameters that are learned. And we're just talking about, and if you're talking about a deep LSTM, that is 3 or 4 or 5 layers, then the number of parameters to be learned increases exponentially. It basically has a quadratic complexity. So what is already such a complex network, we are adding more parameters to be learned, mainly the aspect embeddings, which is the additional parameters that this network has to learn. And if now if the aspects that have to be learned are let's say not 10 but 100, that increases the complexity so much more. So the one drawback, or maybe it's required, but one slight drawback is that more parameters means more complexity. I have some thoughts on what we can do about it. On the accuracy part, I feel the authors used plain unidirectional feed-forward RNNs, but because these are restaurant data and these are not streamed in real time, I feel that maybe we could try with bidirectional RNNs. So, for example, the same 10-word sentence. And word one's information is passed on to word two and so on, like we saw. But what bidirectional RNNs do is the information is both forward and backward. So that makes the training so much more robust. So that may be something, in fact, I want to try before the end of this course to see if bidirectional RNNs have any significant improvement in the accuracy scores. Regarding the complexity, I actually feel that maybe GRUs could reduce, could help manage the complexity by reducing the parameters to be learned. To give a small overview on what a GRU block and how is it different from LSTM is, let's look at this picture. In LSTMs, we have three gates: input, forget, and output. But a GRU kind of simplifies that by having only we can still, these are not specifically called input and forget, but input and output, but basically does away with the forget gate, and the output is basically 1 minus zt plus 1 minus zt into hidden layer output plus z into hidden layer output. So it's basically doing away with one parameter, one set of parameters that have to be learned, because the weights and the bias of the required embedding of the required vector size. So since GRUs reduce the parameters to reduce one set of parameters that have to be learned, maybe it will help manage the complexity by accommodating the learning that is required for aspect embedding. And my hunch is that maybe by reducing one, by taking out a parameter that has to be learned and adding more, I hope the computation complexity kind of balances out. So these are the two things that I strongly feel can be explored to understand, to see if we can improve upon both the accuracy and the computation complexity. With that, thank you very much for watching so far. Bye.